hold on a second. Greater than, but less than b. Okay, so from here to here, all I did is I made the event. This event is contained in this bigger event, as I wrote down over there. And so this is 1 less often than that is 1. You know, for any, whenever this is bigger than a, I get a 1. Here I only get a 1 if you're strictly less than b and greater than a. Right? And now you can see I can kind of get away with murder because this thing here is so tightly constrained, right? You know? I've got, under this event, this average is less than b. All right? And so, so this average is greater than what? And there's a, oh, wait a second, there's a minus sign missing somewhere. Where is it? Q theta over p. Shit. Somebody, there's a typo here, guys. There's a minus sign missing, right? Wait. Isn't there? Maybe not. Hold on. Hold on. Yeah, yeah. I need this on the other side, everyone. P is Q times this is a negative sign. I have to bring this to the other side. So there's a minus sign missing there. And there's a minus sign missing there. All right. All right? Because I said that you can flip this around. We know that, you know, P is... Yeah. All right, so you can just take it to the other side. All right, so there's a minus sign dropped. So I've got a minus sign there and a minus sign there. So I've got that this average is less than b. So I have that so this is 0 unless this average is between these two bounds, right? So and theta star is positive. We were maximizing over theta greater than 0, all right? So I can replace this f by b to get an upper bound. So on this event, when this is 1, this average has to be less than b. All right? So I'm taking the theta star as a constant, comes out, and we're replacing the average of f by b, its upper bound. You know? For if this is not hold 0, I just don't care about it. It gets killed off anyway. All right? So there's a couple of things I'm doing there. You know, I'm taking the theta star outside. That's a constant. I couldn't care less about it. But the sum of f of yk is less than, you know, n times b. Whenever that is 1. You can't leave this room until you all understand that. Right? This thing can take on all sorts of values, but if this average is between B and A, you know, then I've got, that's my, you know, this thing here is just that, you know, and it's got an average of the F's in there. The average of the F's is between A and B, right? And the biggest it can be is B, so I get an upper bound here, but then I realize there's a minus sign there, so I get a lower bound here. All right, this whole thing, it's a number. It's not random anymore. It's just e to the minus that. All right, that is greater than that. This whole thing, even though it's random, I replaced it by a deterministic bound. You know, this bound is not random anymore because of the fact that the average of the F's, the sum of the F's, is less than or equal to n times b because of this this here. All right. Now what? Well, I can take logs and then take limits, and I'm not going to get what I wanted. I'm going to get a b instead of anything. I mean, this average is going to come to some number. It actually goes to 1/2. By the center limit theorem. You can actually interpret this as like a CLT sort of thing. And this thing here converges to 1/2. So in the notes, I went through excruciating detail to explain that and gave you a formula for it. Here I won't prove it, but it's in the notes, just said in actually much more detail. I'll explain why in a bit. So this thing converges to 1/2. So when I take a log, I get a log of 1/2. That's going to disappear. Again, so I take the log of this monster, which is the sum of the logs, and the log of that, a log of 1/2, I'll ignore that. The log of an exponential is itself. I divide by n, I get minus sign. I'll get a minus theta star b minus lambda for theta star. So what is it again? Yeah, theta star b okay, and you see that I'm really crucially using the fact that because yk is distributed according to q star, so this event is not an unusual thing anymore. That's the whole point. I've zeroed in a world where being in the strip is typical. You know, half the time I'm to the above it, half the time below. The CLT says that. You know, CLT I know has one of a square root of n, but you normalize things, and if you look at the probability of being positive, being in this half space, the CLT tells you it goes to 1/2. It's the simplest example of the CLT you can think of. Right? And so I'm using the fact that this event becomes typical when I make this change of measure. And this thing going to 1/2, take a log, divide by n, disappears. This thing is my gold. And you know, as I said, I didn't want B, I wanted A. You know. All right, but this is any b which is bigger than a. And that's a typical way you cheat in this thing. If something is lower bounded by, something, a function of b, for any b, you can creep upwards and make it true for a as well. Okay, it's a standard thing. And that's what we already decided was the rate function. Okay, happy face, that's it. So it's that simple. And it really is I know, I used a few sleight of hands here. There's the likelihood ratio trick. Absolutely fundamental. You'll play around with that. If you stay in this sort of world, this will happen all the time. And then applying it to make a change of measure, to make something unusual into something typical. Absolutely a fundamental concept that's used a lot. And then it worked. In this case, you get this result. So that's it. So in the notes you'll see I did all sorts of weird things. I didn't fix b. I made this thing crush downwards as n got larger. And the reason for that is that in my mind, when I wrote these notes the first time 10 years ago, I thought it was sort of a way to get a hint you can get better bounds. So by letting b go to 0 with n, you can actually get rid of the log. You can actually, it's amazing. You can actually sort of almost compute this thing. And you get something that's, basically, instead of applying, you do a finer central limit theorem on this twisted thing, you can get a finer large deviation principle. And that comes up a lot in some statistics applications. All right. So basically, I did more in the notes. And if you're interested, read them, and it might be interesting. But questions? I did it. It's not easy. Yep.
So we have this geometry.
Yeah.
So this geometry was built on the fact that f was L. The likelihood.
Well, we made it L.
Okay, so
See, look, it is L. There it is. That's L.
okay.
Yeah. No, that's the whole point. Is that you have a problem, and you create a log likelihood ratio to fit that problem.
So this
Yeah.
is true for a likelihood ratio. So for f is a likelihood ratio.
No. Remember the problem? We started with an f. The question was, we want to bound this probability, which is the same as bounding expectation, and f was given. And then the thing is, well,
We build a thing.
through some crazy genius 100 years ago realized if one particular probability measure would make this really typical, the empirical distributions would flock to this point. When this rare event happens, the empirical distribution is going to flock there. And I'm sort of making that precise by doing this.
So
Yeah.
the Q is dependent on f.
Absolutely, right there. Yeah, right there. There it is. Yeah. P and Q are related by this likelihood ratio.
So f is likelihood function for p and q theta.
So, well, not f, but this,
Yes,
the theta star. This is the likelihood ratio. Or this is the inverse likelihood ratio, whatever. Depending on who is the center of the universe. So given f, we define a likelihood ratio and do it. And then again, that's a typical machine. That's like, you're not given the likelihood ratio, you actually construct it by, based on the problem. I love this stuff. I don't know. I'm just sorry if you don't. Yes.
So
Yeah.
CLT assumes that as n gets really large, Gaussian's a good model. But here,
Yeah, and that's why it's a baby version of
we
CLT.
have more wiggle room,
Oh, yeah. I mean,
large deviation, right?
no. LDP, they're different planets.
So if imagine
Yeah.
we have we want a large, we want to calculate the probability of that sum Sn over n is greater than or equal to a very large number. If it's a very large number, then it might be really poor, right?
I don't know how to answer that. I will say this. maybe I did say this before. Yes. The CLT looks a lot like the LDP. I mean, you can write it this way. It's not obvious, but you can. Because you can take the A inside here to center Sn, and then you multiply both sides by square root of n. You get the CLT question. And so this gives you a limit for this in terms of a Gaussian random variable whose variance is the variance of x, right? So that's how they're related. And I think that it's in the information theory community, I think it's recognized now that this is a way more reliable way of getting bounds than the large deviation principle, you know? So if you want to get confidence bounds in a simulation or something, this is it. It's really magnificent. And
it's like really far away from your mean value, like say the number.
It depends what you mean. You see, I mean, I don't know. I don't know how to answer that question. Yeah.
It's like a really rare event, like truly.
Well, that's the only thing you. I mean, no, but look at this. I don't know how to say it. I mean, you know, you can B0 can be arbitrarily large, you know. But you have to fix it and then let n go to infinity. Yeah, I don't know how to answer that. I just know that in my own, when I've done simulations myself, my own research, and I know that in the broader information theory community, it's sort of, it's dogma that this is a really large, if you're looking at confidence bounds for simulation, and this is a monster. And so like the applications I gave you, the geometry of hypothesis testing or communication theory, that's where it's like a really valuable tool, I think. Outside of that, I don't know. Yeah, I've been very unlucky applying large deviations to getting bounds, you know, like a simulation environment, something like that. Just, I think it just, and it has to be really large for this to kick in. Yeah. So I didn't spend so much time in this because I think you all are going to care about large deviations the rest of your life. Again, I did it right there. I wanted you to see this once in your life. Right? Yeah. Yeah. So, yeah. But the philosophical questions, I'm scared to say anything absolute. Yeah. Yeah. So, all right. That it? Okay. So on Tuesday we'll get into another subject. I guess it's going to be linear estimation and stuff. I don't know what I want to spend that much time on that because it might put us all to sleep. But we finished this sort of limit theory part of the course. And I'm sort of in adaptive mode. So Aditi and I will do some soul searching. And anyway, look at the syllabus. We'll be roughly following the syllabus as we have it. All right, have a good weekend.